new live stream, and today's topic will be recursion. Actually, I should know it already because I did the merge sort, but we're gonna redo it, right? So I'm super hyped for that. Here we go. Let's dive into this topic. Let me see. Go there. Probably you're also hyped for my English. So here we go. Recursion. A recursive function in C++ is a function that calls itself. Here is an example of poorly written recursive function. Why it's a poorly written? Okay, we have a void, we have a countdown, we have then an int count, whatever. And wait, let me fix a little bit more the chat, right? We need a little more bigger if someone writing something legit. Something like this. Right, and then, yeah. I think this is okay. I can go a little bit more down. I don't know. This is okay. Okay, let me see. Countdown, integer count, and we have std out push count, so ever countdown, and we're gonna call it again, right? And then we decrement it like with -1. Countdown call itself recursively, so we keep doing it. So and here we're gonna call it, right? Countdown 5, the integer is 5. We're doing it 5, 4, and we keep doing it. So if we have this thing, it will not gonna stop, right? No, we have no return, nothing. It will not gonna stop here. So we keep counting, correct? Yeah, probably. That's why it's a bad one. When countdown 5 is called, push 5 is printed, and countdown 4 is called. Countdown 4 prints push 4 and calls countdown 3. Countdown 3 prints push 3 and calls countdown 2. The sequence of the countdown n calling countdown n -1 is repeated idem. What this means? I have to how to pronounce it correctly. Sorry, guys. I'm also learning English.
Indefinitely,
effectively forming the recursive equivalence of an infinite loop. Okay, seems like YouTube is working. Let me check quick. Let me check if it's working or not. Yeah, it's working, right? Everything is fine. Everything is working. So we effectively forming the recursive equivalent of an infinite loop. Yeah, exactly. That's what we're doing here, right? In lesson 20.2, the stack and the heap, you learned that every function call caused data to be placed on the call stack because the countdown function never returns. Okay, this is really interesting. You learned that every function call caused the data to be placed on the call stack. What is a call stack? Maybe I have to redo this also because the countdown function never returns. Okay. It's just calls countdown again. This information is never being popped off the stack. It's gonna stay on the stack. Now I'm getting it. So consequently, at some point, the computer will run out of stack memory. Stack overflow will result, and the program will crash or terminate. On the author's machine, this program count down to -11,732 before terminating. Okay. Nothing special here. Nothing special. Everything so far so good. Recursive termination conditions. Recursive function calls generally work just like normal function calls. However, the program above illustrates the most important difference with recursive functions. You must include a recursive termination condition, or they will run forever, actually until the call stack runs out of memory. A recursive termination is a condition that, when met, will cause the recursive function to stop calling itself. Recursive termination generally involves using an if statement. Here is our function is signed with a termination condition and some extra output. Okay, let's gonna see. So we have still the countdown, then we have integer count, we have the 5 here, and then we have the see out if count is bigger than 1 or what? Really? Okay, termination condition. Yeah, okay, then okay, got it. So if we hitting the 1, if count is bigger than 1, everything is fine. If it's not bigger than 1, not gonna call it anymore. The problem will not have to state if it's equal, right? So if it's 1, it's not bigger, it's not equal, so it will also stop. So we're counting only to 2, right? Termination condition, countdown, count minus 1, and so on. Everything is clear here. Now when we run our program, countdown will start by outputting the following. Oh, I was wrong. We're pushing back 1. Really? So we have 5, 4, 3, 2. Ah, okay. It's the push, right? Not the... Ah. Okay, if that would be the other side, I mean, we could check it, right? Let's see. Like this, let's open up front wall. Here we go. Ah, that was something different. We can talk later about this topic here. So, now I have to add a compiler or something. Add new, execute. Okay. Here, hop is 1, 2, 3, 4, 5. Okay. Can I have it on the right side, please? Give it something like this. Okay. What is... Let's also count. So we have the first... Wait, why am I confused right now? Exactly, this is the 5 first, then we have 4. Then we have this statement. It's calling itself again. So it's minus 1, so it's 4. Why is this stuff always confusing me kind of a little bit, you know? I don't know why, but it's like always a little bit magic for me. Probably I have problems to visualize it. So I'm getting this one, so we keep going into the dab because it's recalling itself, then with 4, then with 3, then with 2, then this 1, right? So if this here, we're calling it again, and it will be 1. 1 is not bigger than 1, so we're still gonna print it out here. That's everything is correct. Why I'm confused about this statement here? So if you have this first thingy, if this statement is not true anymore, right, then we have, for example, 1. Why am I confused with this pop thing? Pop thing is 1, 2, 3, 4, 5. I'm getting the 1. Not really. Yeah, I'm getting the 1. But why are we getting the 2? Man! I mean, we're doing this And after this, we're doing this. So, okay, I got it. So we will have 1, then we will have the 2, then we will have the 3, then we have the 4, then we have the 5. That's the reason. So we're starting with 1, 2, 3, 4, 5. But why are we getting even... Why we even push back the 1? I get it. Why we are able to push back the 1. If we have the 1, right, and this is even ending, we're getting also this one. That's why this is working, right? This is actually really important to understand this here. With the countdown, and if you're not hitting the statement, if you even have the 2, you will have still this. This is getting called. But still, I have problems sometimes to visualize it. When what is gonna get called, you know what I mean? So this is because I think I'm in the layer, right, of that one. I don't know. Well, I think I need someone that is gonna help me to visualize it. Why I have problems to visualize this? Because I think I'm just in one step deeper into the layer. And then I have like the feeling we're doing that, and I have the feeling we're still calling them the pop, right? But if that would be the case, we not have like first push 5, push 4, push 3, push 2, push 1. We would have then, I don't know, push 5. And then why is this confusing me? It's funny. I think what is confusing me that if we're going one step deeper into the layer, that this is gonna get called, right? And it's still doing something in the layer, right? You getting my point? Maybe I'm overthinking here the process. I think this is the problem. I mean, this makes completely sense. 5, 4, 3, 2, 1. And then this statement is not true anymore. Then we call pop 1. And then the other ones will come magically. 1, 2, 3, 4, 5. What? Okay, we're gonna read it. We're gonna read it. Now, when we run our program, countdown will start by outputting the following: 5, 4, 3, 2, 1. Done. I got it. If you were to look at the call stack at this point, you would see the following. Oh, this is interesting. So we have countdown 1, countdown 2, countdown 3, countdown 4, countdown 5. Okay. It makes sense, right? Because we have first this, that, because it's the stack. This helps me a lot with the visualization. Because if I have the 5... Okay, let me read it. So because of the termination condition, countdown 1 does not call countdown 0. True. Instead, the if statement does not execute, so it's print pop 1. Correct. Got it. And this is getting first called. And then we have countdown 2. Oh, this is so good. Pop, yeah, exactly. And we have that one, right? This calls then, what is it, like the pop one, and then we have that one, and this is gonna call then. Yeah, then I would expect, if I have countdown, I would expect that I'm printing count and then the push, and that makes actually no sense, right? Am I right? Am I wrong? Let me see how they're gonna describe it. So if the statement does not execute the print pop and this terminates, at this point countdown 1 is popped off the stack. Yeah. Are we just popping it off after? Okay, it's not gonna stay anymore because we have no loop anymore then there. Because it's not calling it itself anymore. And control returns to countdown 2. Countdown 2 resumes execution at the point after countdown 1 was called. So it prints pop 2 and then terminates. I'm still missing something. I'm still missing something. So that makes sense to me. Right? If it's if you were to look at the call stack at this point, you would see for a ring. I mean, that makes sense. Let's explain me how. Am I missing maybe this topic? Oh yeah. Maybe I should read this before. Okay, let's do it, right? Is it a big topic? Oh, it's looking big. But it seems I needed to understand it, right? So we're gonna go through this topic quick again. The stack and the heap. The memory that a program uses is typically divided into a few different areas called segments. The code segment, also called a text segment, where the compiled program sits in memory. The code segment is typically read-only. The BSS segment, also called the uninitialized data segment, where zero initialized global and static variables are stored. The data segment, also called the initialized data segment, where initialized global and static variables are stored. The heap, where dynamically allocated variables are allocated from. The call stack, where function parameters, local variables, and other function-related information are stored. For this lesson, we will focus primarily on the heap and on the stack. And that is where most of the interesting stuff takes place, the heap segments. Okay. The heap segment, also known as the free store, keeps track of memory use for dynamic memory allocation. We talked about this heap a bit already in lesson 19.1, dynamic memory allocation with new and delete. So this will be a recap. In C++, when you use the new operator to allocate memory, this memory is allocated in the application heap segments. Yeah, that makes sense. PTR assignment, nothing new here yet. Assignment 4 bytes in the heap, and then we have that one, the same, right? Areas assigned 40 bytes in the heap. So good so far. The address of the memory is passed back by the operator new and can then be stored in a pointer. Do not have to worry about the mechanics or mechanics? Mechanics, right? Is it mechanics? It is.
Mechanics.
Yeah, mechanics, right? Behind the process of how free memory is located and allocated to the user. However, it is worth knowing that sequential memory, sequential, I don't know. I have to check.
Sequential.
Memory requests may not result in sequential memory addresses being allocated. Okay. Okay, PTR1 and PTR2 may not have sequential addresses. Oh. Oh. Okay, interesting. When a dynamically allocated variable is deleted, the memory is returned to the heap. Okay, got it. Okay, the memory is returned to the heap and can then be reassigned as future allocation requests are received. Remember that deleting a pointer does not delete the variable. Makes sense. It just returns the memory at the associated address back to the operating system. The heap has advantage as advantages. Allocating memory on the heap is comparatively slow. Okay. Allocating memory stays allocated until it is specifically deallocated. Beware memory leaks or the application ends, at which point the OS should clean it up. Should. Good word. Dynamically allocated memory must be accessed through a pointer. Dereferencing a pointer is slower than accessing a variable directly. Makes sense. Because the heap is a big pool of memory, larger array structures or classes can be allocated here. Okay. The call stack. The call stack usually refers to as the stack has a much more interesting role to play. The call stack keeps track of all the active functions, those that have been called but have not yet terminated, from the start of the program to the current point of the execution. And it handles allocation of all function parameters and local variables. The stack is implemented as a stack data structure. So before we can talk about how the call stack works, we need to understand what a stack data structure is. Okay, here we go. The stack data structure. I need what? There's a lot of text. A data structure is a programming mechanism for organizing data so that it can be used efficiently. You have already seen several types of data structures, such as an array or structs. Both of these data structures provides mechanism for storing data and accessing. What is this word?
Access.
This okay, access. Okay, I can do it, right? I can do it. Right. Accessing. It's just accessing, right? And accessing the data in an efficient way. There are many additional data structures that are commonly used in programming, quite a few of which are implemented in the standard library, and a stack is one of those. Okay, consider a stack of plates in a cafeteria. Because each plate is heavy and they are stacked, you can really only do one of three things. Look at the surface of the top plate. Take the top plate off the stack. Okay. Exposing the one underneath, if it exists. Put a new plate on top of the stack, hiding the one underneath if it exists. Okay. In computer programming, a stack is a container data structure that that's why we call it like okay. In computer programming, a stack is a container data structure that holds multiple variables, much like an array. However, whereas an array lets you access and modify elements in any order you wish, called random access, the stack is more limited. The operation that can be performed on the stack corresponds to the three things mentioned above. Look at the top item on the stack, usually done via a function called top, but sometimes called peek. Take the top item of the stack, done via a function called pop. I know what I'm missing, man. Put a new item on the top of the stack, done via a function called push. We're getting closer. The stack is last in, first out. Oh man, this reminds me, guys, on business stuff. First out, first out. Oh, that's so good. Okay, a stack is a last in, first out. LIFO, I don't know, LIFO structure. The last time, okay, stack is last in, first out. Last, first out. Why the last? Okay, then we're taking. Let me think. So last is, so we're putting the last point in or what? And first out will be the first. What we put? Okay. The last item pushed on onto the stack will be the first item popped off. So because we have plates, right, and we're putting a plate on. So, and if we're putting something out, we taking. Okay, got it. If you put a new plate on the top of the stack, the first plate removed from the stack will be a plate you just pushed on last. Okay. So I have different plates, right? And if I'm putting a new plate on it, and it will be also the first one what I'm receiving then, or what? If I'm taking some, if I'm gonna take a plate, I got it. I like this example. It's a nice example, right? Isn't it? If you put a new plate on the top of the stack, the first plate removed from the stack will be the plate you just pushed on last. Last one, first off. As items are pushed onto a stack, the stack grows larger. As items are popped off, the stack grows smaller. Makes sense. For example, here's a short sequence showing how pushing and popping on a stack works. Popping, is it called popping on a stack works? So we push 1, stack 1, push 2, stack 1 and 2, push 3, 1, 2, 3, and then we're gonna pop, we're taking 3. Then we have 1, 2, pop, and then we're taking the. Okay. Actually, I want to read more about a data structure, right? Maybe I need a good book for that. The plate analogy, it's called, right? Analogy, if I'm reminding correctly.
Analogy.
Wait a second.
Analogy.
Got it. Analogy is pretty good. Analogy is pretty good. Analogy as to how the call stack works, but we can make a better analogy. Consider a bunch of mailboxes, all stacked on the top of each other. Each mailbox can only hold one item, and all mailboxes start out empty. Furthermore, each mailbox is nailed to the mailbox below it. So the number of the mailboxes cannot be changed. If we can't change the number of the mailboxes, how do we get a stack-like behavior? This is getting really interesting. This is new for me. I thought I know how the stack is working. So first we use a marker, like a post-it note, to keep track of where the bottommost empty mailbox is. In the beginning, this will be the lowest mailbox. We'll be pulling it up like this. Then okay. On the bottom of the stack, when we push an item onto our mailbox stack, we put it in the mailbox that is marked, which is the first empty mailbox. And move the marker up on the mailbox when we pop an item off the stack. Yeah. Great. Not say yes if you not 100% understand it, right? That's what I learned so far. Yeah, so we put the mailbox that is marked, which is the first empty mailbox. And move the marker up one mailbox. So when we push an item onto our mailbox, like we put, and then the marker goes one up, because we can use the other mailbox if you want to put something in, right? When we pop an item off the stack, if you're gonna pop an item off the stack, we move the marker down. Makes sense. One mailbox. So it's pointed at the top non-empty mailbox, and remove the item from that mailbox. Anything below the marker is considered on the stack. Anything at the marker or above the marker is not on the stack. Wait. When you pop an item off the stack, we move the marker down on the mailbox. It makes sense. So it's pointed at the top non-empty mailbox and remove the item from the mailbox. Anything below the marker is considered on the stack. True. Anything at the marker or above the marker is not on the stack. So if we're not filled in, it's not on the stack or what? Only if we have data in or what? Okay, let's see. We keep going. We keep going. The call stack segments. Maybe someone of you can describe, like, have a good picture for this one or something. It's a little bit weird, the last sentence. The call stack segment. The call stack segment holds the memory used for the call stack. The call stack segment holds the memory used for the... Okay, now some picture would be already nice, right? I mean, the description was really nice, but now some pictures would be... When the application starts, the main function is to push on the call stack by the operation system. Okay. Then the program begins to executing. Okay. When a function call is encountered, the function is pushed onto the call stack. Function call is encountered, the function is call stack. Okay, got it. When the current function ends, that function is popped off. I have a problem right now. Wait. I have to read this again. So we have like the plates, and then we're putting function on the plate. Done, we're taking it again, right? That's how we do it. And if I have recursive, putting more and more plates on it, and then we're starting with the first, with the second. When the current function ends, that the function popped off the call stack. Okay, let's go now again. When a function calls is encountered, the function is pushed onto the call stack. When the current function ends, that function is popped off the call stack. This process is sometimes called unwinding. What? Unwinding the stack?
Unwinding. Unwinding.
Unwinding the stack. Thus, by looking at the function that are currently on the call stack, we can see all of the functions that were called to get to the current point of execution. How I can check it actually? Can I check it with Visual Studio? Is this possible? That would be really interesting, right? Our mailbox analogy above is fairly analogy. What is this? Analogy.
Analogous.
Okay. Analogy above is fairly analogous to how the call stack works. Okay, the stack itself is a fixed-sized chunk of memory addresses. The mailbox are memory addresses. And the item we are pushing and popping on the stack are called stack frames. Such a nice article! A stack frame keeps track of all of the data associated with one function call. We will talk more about stack frames in a bit. The marker is a register. Oh, this is so good! Mailbox, okay. Stack frames. The mailboxes are memory addresses, and the items we are pushing and popping on the stack are called stack frames. A stack frame keeps track of all of the data associated with one function call. We talk more about stack frames in a bit. Did we have maybe a good picture about the stack frame? Image? Let me see. Oh, this is so good. Okay, what is a stack frame? This is then a stack frame or what? Global frame and then okay. Oh, you can't see it. Is this a stack frame? Like x equals 3, one of these is a stack frame. Stack will store variables or objects and it will call each variable by top of stack by returning because it works on the last in first out. Wait, is this even correct? I will keep reading. I don't want to get confused now. So, a stack frame keeps track of all of the data associated with one function call. We will talk more about stack frames in a bit. The marker is a register. All small pieces of the memory in the CPU known as the stack pointer, sometimes abbreviated as P. The stack pointer keeps track of where the top of the call stack currently is. We can make one further optimization. When we pop an item off a call stack, we only have to move the stack pointer down. True. We don't have to clean up the zeros, the memory used by the popped stack frame. The equivalent of the emptying the mailbox. This memory is no longer considered to be on the stack. The stack pointer will be at or below this address, so it won't be accessed. If we later push a new stack frame to this same memory, it will override the old value we never cleaned up. True. I remember back then we had like a discussion about this topic, but still it could be if you have the address and if you even like freeing it, right? That the data could be still there in the address, right? So, but if you putting something new on this address, it will just gonna be overwritten. But it's still the data will still be there. The call stack in the action. This is such a nice article. Who wrote this? This is so good. The call stack in the action. Let's examine in more detail how the call stack works. And no picture, right? And I think I'm understanding it. Here is the sequence of the steps that takes place when a function is called. The program encountered a function call. A stack frame is constructed and pushed on the stack. Yeah, the stack frame consists of the address of the construction beyond the function call, called the return address. Yeah, this is how the CPU remembers where to return to after the call function exists. Exit. Oh, how to pronounce this correctly? How to pronounce this correctly?
Exit.
Exit. All function arguments. Memory for any local variables. Saved. Okay. Since we are on the end, we're gonna have this return. Okay. Save copies of any register modified by the function that need to be restored when the function returns. Saved copies of any register modified by the function that needs to be restored when the function returns. The CPU jumps to the function start point. The instruction inside of the function begin executing. When the function terminates, the following steps happen. Registers are restored from the call stack. Okay. The stack frame is popped off the stack. What this means, registers, what's a register was again the mailbox, right? The marker is a register. Okay, the marker was, okay. Then we have restored from the call stack. Okay. The stack, okay. Okay. Function terminates. Sure that I'm understanding this. Okay, correct. Stack frame is popped off the stack. This frees the memory for all local variables and arguments. Okay. The return value is handled. The CPU resumes execution at the return address. Okay, so far so good. Return values can be handled in a number of different ways, depending on the computer architecture. Handled in a number of different ways, depending on the computer architecture. Some architectures include the return value as a part of the stack frame. Okay. Okay, other use CPU registers. Okay. Typically, it is not important to know all the details about how to call this stack. I think it is important, right? Isn't it? However, understanding the function are effectively pushed on the stack when they are called. And popped off unwound when they return give you the fundamental needed to understand recursion. When they return gives you the fundamental needed to understand recursion, as well as some other concepts that are useful when debugging. A technical note, on some architectures, the call stack grows away from memory address 0. On others, it grows towards memory address 0. What? As a consequence, newly pushed stack frames may have higher or lower memory addresses than the previous ones. Wow, this is crazy. A quick and dirty call stack example. Consider following simple application. Okay, now we're gonna check this. That was clear, okay. So we have food and we have integer x, return x. So that means here, if we're gonna call it, we are pushing it on the stack. Who is pushed on the call stack here? Yeah, we're gonna do it. We push it here, and then it's gonna end, and then we're gonna free it, right? Terminating, return x. Who is popped off the call stack here, right? That's what we're doing here then, until that one. Exactly. A, B, C. What is the B? It's describing. Yeah, okay. The call stack looks like the following at the label. How I can see the call stack? So the call stack looks like the following at the labeled points. So this is main. Then we have B, and with foo including parameter x. Yeah. Exactly, and then main. Then we have C. This here is then a main again. Okay. Stack overflow. Here we go. Stack overflow. The stack has a limited size and consequently can only hold a limited amount of information. On Visual Studio for Windows, the default stack size is 1 MB. With G++ client for Unix variants, it can be as large as 8 megabytes. The program tries to put too much information on the stack. Stack overflow will result. Stack overflow happens when all the memory in the stack has been allocated. in that case, further allocation begins overflowing into other section of memory, and we know this is super dangerous. Stack overflow is generally the result of allocating too many variables on the stack and or making too many nested function calls where function A calls function B, calls function C, calls function D, etc. So nested is also like, can be bad, right? On modern operation systems, overflowing the stack will generally cause your OS to issues and access violations and terminate the program. Okay. Oh. Here is an example program that will likely cause a stack overflow. You can run it on your system and watch it crash. No. That's such a meme. I'm not going to do it now, guys. Okay, we have the stack. Okay, integer stack. And then high. And then stack 0. And then return. We will use stack 0 here so the compiler won't optimize the array away. Oh, this is like... Okay, got it. Oh, that's so funny. This program tries to allocate a huge, likely 40 mbit array on the stack because the stack is not large enough to handle this array. The array allocation overflows into a portion of memory the program is not allowed to use. On Windows Visual Studio, this program produces the result hello world exit proceeds blah 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 exciting. Okay, got it. Like this number here. Yeah. 10,000 whatever is in hex, which is in Windows OS code for access violation. Note that high is never printed because the program is terminated prior to that point. Makes sense. You're not able to go there. Okay. Here's another program that will cause a stack overflow for a different reason. To read yellow emo for the idea for adding a counter. Okay, G count. Okay, we got it. And we have eat stack. This guy is a legend, man. This article is so good. So we have stood C out, and then we just counting it up this way. Yeah, and we use a conditional here to avoid compiler warnings about infinite recursion. G counter, if G counter is bigger than 0, it will be already bigger than 0. Not that each stack calls itself, so we keep doing it, calling, and so the stack will grow and grow and grow and grow. Needed to prevent compiler from doing a tail call optimization. That's why we're doing that one. Oh, he is exploiting it, man. He's exploiting it. In the above program, a stack frame is pushed on the stack every time function each stack is called. Since each stack calls itself and never returns to the caller, again, in the above program, a stack frame is pushed on the stack every time function. Yeah. Since each stack calls itself and never returns to the caller, eventually the stack will run out of memory and cause an overflow. Author's note: when run the author's Windows 10 machine. From within the Visual Studio Community IDE, each stack crashed after 4,848 calls in debug mode and 128,679 calls in release mode. Not bad. Related content. We talk more about functions that calls themselves in upcoming lesson recursion. I think now I know why I don't really understand recursion. Listening to this as a Python dev, I'm like running out of memory. Ooh, okay. What do you mean with that? Like, how is it in Python, by the way? How is it in Python? So the stack has advantage of this and disadvantages. Here we go. Allocating memory on the stack is comparatively fast. Okay, memory allocated on the stack stays in scope as long as it's on the stack. It is destroyed when it's popped off the stack. Makes sense. All memory allocated on the stack is known at compile time. Consequently, this memory can be accessed directly through a variable. Okay. Is this bad? Is this good? Because the stack is relatively small, it is generally not a good idea to do anything that eats up a lot of stack space. This includes allocating or copying large arrays or other memory-intensive structures. Why is the stack actually not bigger? Why is the stack not bigger? So now we're going back to the topic recursion. So I had like the problem to understand what was the problem? This here, right? That we have push 5, push 4, push 3, push 2, push 1. Right? But it makes sense now. It makes so much sense why it is how it is, right? So we have that, it's calling itself. Because we're taking first this plate 4, 3, 2, and 1, and then we're taking it off. And then we have pop 1, pop 2, pop 3, pop 4, and pop 5. But here in this example, we have no return time, right? That's why I'm a little bit confused with void. Can maybe someone help me here? In Python, you don't have to allocate memory. Yeah. Maybe I should hop on Python, huh? Python. I think, yeah. We all know why we're learning C++, correct? We're learning C++ that we actually can flex on people. We not have to need to be productive. I'm just kidding. So I still have here a problem because we're not returning something. You know what I mean? Here we're returning the X. And I think maybe I don't know how void is working, right? So you don't need to return from a function. So if the function will like get terminated from the stack, right? So I have a problem how we going into this layer. Why is this pop getting called later? You know, I'm getting the point, but this is not my return value. You know what I mean? That's why I'm a little bit confused. Is it like, okay, if we're hitting here the termination condition, then just keep calling this and free the space? Probably it is like that, right? So we're taking the first plate on the stable on the stack. Right? It's probably like that. So we building it up. And then like, okay, we want to terminate it. We have still this call here, right? We have still that one. So then we have pop 1, pop 2, pop 3, pop 4, pop 5, right? LIFO. Here we go! Okay, Edward, I had like, I can't talk about this thing, but I had with the guy a huge discussion. And it seems like he was also like not that happy. It was not on stream. And he said to me that, wait, where's my pencil? That this or this make no difference. No. I said, okay, if you're using, for example, if you're using this here, right? If you're using I++, we generating a temporary copy, right? If you're using this here, we're not going to generate a temporary copy. I know we have compiler optimization. I know this, right? I know this. But by definition, is this statement correct? So, I tried to prove it, and I had like problems to prove it because of the optimization of like the compilers. Then I did this. I'm gonna show you. Where is it? No! Wait. I have it still because I sent it to a friend of mine. This is a little bit off topic, but it's also interesting. You see that? So I could I have to do it with this A. Otherwise, you can't see in assembly that you're gonna generate a deep temporary copy, right? And that's what we're doing, right? We generating here a temporary copy with I++. You see that? And if we comparing it with that one, increment, pre-increment, right? Then we're not generating a temporary copy. It's assembly, yeah. But the code produce a different results. What do you mean? You don't know how to read assembly because he said, okay, if you think if you're right, check the assembly code, right? And I was like, okay, I know by definition if I'm putting like for example the A away, right? I'm gonna show you. I'm doing it like this. The compiler will just optimize it away, so it's the same, So I have to trick a little bit the compiler. Because if I'm understanding it correctly, if the return value is not getting get used, it's just choosing the other one or something like this, So here we have again this temporary copy. Wait. The second one will never loop and the first one will loop? Why? Okay. Wait, what are you saying? No, you don't seem to get it. The second one will never loop and the first one will loop one. The return value will be 6. Okay. Yeah, okay. I mean, I could just do an I, right? Okay, then make it 7 or something, right? But then you have the same thing. So we're still generating a deep copy here. But now one loops one more than the other. Oh man, okay, I like this. Still, you're generating, it's just the point that you're generating here temporary copy. This is not the same. Why? Wait, let me see. So if you have that one, we have A, it's not defined. We say I++, so it's then the 5, right? We have 5. 5 is smaller than 6, so we doing one rotation. So if we have that one here, we have 4, 5. Okay, this is not going to work also. Because... If you're doing that, A will be 4, correct? That should be now correct, right? Okay, what I have to do if... how I can fix... So because A equal 5 in line 9 and the first one will be 4. Wait, which one? First one or the second one? That I made? But the standpoint, even if it would loop, we would generate this kind of temporary copy, correct? Yeah, I know, but okay, wait, I found something on. So okay, if we have the I++, and the I++ would be a function, right? If we wait, I'm gonna draw it quick. So if we have wait, drawing time, boys. If you have I, the line is too big. I can live with that. So if you have I++, right, and that would be a function, right? Then we would return. Then we would return the old value. Right? Now we would create a new way. Okay, we would say, okay, temporary, and that would be, for example, I, and then we would return I, but we would say I is I plus 1, something like this, right? And I know that's not super beautiful, but if I have like then a function that called like something like this, I, and then I would just say E is equal E plus 1. Actually, if we can just return it like this. Return this like that, and then we have it, right? Is this correct? And that's the method. That's the reason why you said yesterday to me for my for loops I should use this method, the increment thingy, right? Because here you would always storing data temporary. Correct? Am I correct or am I wrong? Okay, wait a little bit. No, you don't get the point. You will never see it in a modern compiler as long as you don't use it. I know this. That's why I did this like the thing with the A. But when you use it, you cause different behavior. So either you see something, but it's just different, or it is the same. Okay. But it's better to use this one, right, for loop. Correct? It's better to use this here. Yes or no? I think his point is that either work in different ways or the optimization makes them the same. But I read if the I would be an object and you would do the plus plus, then you will not have this kind of optimization. Depends on the object, how it's defined, correct? Yeah. And that's why it is good to write plus plus I, correct? In the for loop or in a while loop, whatever. If you're not gonna use this value, then you're gonna write it like that. I just said theoretically that if you're using I plus plus, that you're gonna store the value temporary. And I said, but I know it will get optimized if you're not gonna use the value. I said this. Just continue now. Yeah, but I want to know who. He just said there will be no temporary copy or whatever. You know, it's actually the same. I mean, this answer is for me like just too casually. I mean, there was on Stack Overflow was a good example about this topic. Where is it? Browser. We have the browser open. Let's see. Stack Overflow. Plus plus I versus I plus plus. No, that was not a. No, there was a better one. Was a better one. Was it one with drawing or something? No, that's not right. I'm not finding the article. Flag an unused return. Okay, it's where you wouldn't need to write a compiler or read about how a compiler works to get the point. Flag and unused return values from a user-defined non-default postfix operator ++ or operator --— function. Prefer using the prefix form instead. User-defined non-default is intended to reduce. Oh, this is reduce noise refresh. But So, okay, guys, why you told me then yesterday I should write ++ I if it's actually not matters? Huh? Why I should do it then? Please explain. Yesterday someone said it. I got today completely roasted. You just follow standards and you're good. Okay, what is the standards? To say ++ I or what? Is this the standard? In a for loop to use +++? Hey, Kek Wiggler. How are you doing? Is this the standard? Yes or no? But in for loops, you're using I++ or what? Yeah, is the ++I? Why are people preferring the ++I? Guys, if someone is good at MATLAB, maybe someone have time to help Kek Wiggler here to learn for the exams. Next Monday, if I'm remembering correctly, right? I mean, I got completely roasted. I just said there will be a temporary. I want to. I mean, we had yesterday a deep talk about it. No one is dumb. And you are correct with that way, in a way. So I'm correct, right? I mean, I got brutally I got like roasted. I mean, I just said there could be a temporary copy. That's why it's better to use, well, some people prefer to use ++i, but in most cases, the compiler can handle the situation not using the return value. And he just said, that's not true. So do you have a way how I can prove it? I mean, did I need even the loop to proving it? Let's see. No. Right? Right, I have to read it. Yeah, you can see I'm generating. Yeah, that's the proof here. I'm generating a copy with this I++ one. A temporary. I know they are not the same. They're returning different values. This is the returning the old value, so that's why we have this this lias thing, right? And this is just adding a +1, and that's it. So okay. So if we have, guys, you're killing me today again. If we have a while loop, is it 1 0? It was while 1 1 1, yeah. And we could say, this is not working. I can't do it like this, and I can't prove it. I'm not able to prove it. Can someone prove it? Prove this thing? Because if I'm putting here the I in and doing that out, it's not gonna work because the variables are just differently. Because it's just getting optimized away, right? So I can't prove it. Just the compiler is gonna optimize it away, right? Because if I'm not gonna use it, if you're not gonna use the return value, it's just gonna optimize. Did I saved it maybe? So guys, I need help because I want to be right. You teach me that, this is generating like, but from the logic, from the definition, but from the definition with how like operators working, right? If I have this I++, I have to store another value, correct? I have to store it because I'm returning something else. So if you have the argument that the one thing is not the other thing, so okay, we're making it even simpler. Can I say that the I++ plus plus and the plus plus I, right? Watch out. Can I say that this method here generate more overhead than this method here? If oh man, the compiler, if this is assigned to a variable or something, right? If the return value get used. Oh man. No, it was not that one. Assign increment assign. No, it was not that one. And so now first element is done and the value is assigned. Okay, this is like the standard what you're also learning. I had like something else. Has the same effect. Many times there is no difference. Oh man. Okay, ich hab mich blamiert, Alter. Difference are clear when a return value is assigned to another variable or when the increment is performed in condition with other operation. Precedence applied I plus plus 2 different. In many cases they are interchangeable. A classical example is for the loop syntax. Has the same effect. Efficiency. Pre-increment is always at least as efficient as post-increment. In fact, post-increment usually involve keeping a copy. Yeah. Of the previous value around and might add a little extra code. It's might, right? I said that. So was my statement today correct? I mean, I don't want to get roasted another time. Okay, my statement is correct. Because he just said I++ and plus I is kind of the same if you're using it for the for loop. And that just argument, it's not, it can be, it might be that the post increment can be slower, could be slower in some scenarios because it's adding a little bit overhead. And he just said no. There is no copy. I mean, and there was even no argument. There was even no argument for this no, you know? A person just said it. The thing is, I can't prove it. I try. The problem, I can't prove it because the compiler is optimizing it away if I'm not assigning something to the return value. And that's my problem, right? But maybe here we have a lot of smart people. Maybe someone of you guys. Huh? If you have a way to show that, please. Yeah, I tried to do it, you know? So for example, if I would have like a while loop and would say, if I would say this one, for example, you know? Wait, can you see it? Yeah. Left the while loop and I would say I smaller than 2, right? And here I would do the same. I is smaller than 2, right? And then I'm not gonna use it. That's the problem, right? Now it's gonna get optimized away because it will be the same. The heck? Why are we getting an error? Because of the A. Oh. Am I missing something? Should be. Okay, guys, and here we have an I. And here we're missing something like this. And now you see it's optimized away. And this statement here, what you can see, it's actually is deactivating the optimization. And you can see this is literally the same. Yeah, I have something in the back of my head as well about some C++ Weekly, but good damn, I don't want to look up that shit. It really doesn't matter right now. This is an argument you can have with people who are like 10 years in this shit, and depending on the existing code, both sides might be justified. Or YouTube videos. There's so many bad stuff about C++ out there on YouTube, and like even content. Like, this is insane.
Hello and welcome to C++
What's this?
Weekly. I'm your host Jason Turner.
I've watched this already.
In your code gen.
Oh, this is good. This guy is good.
and-
We're gonna watch it. Okay, we finishing recursion, right? And then we watching this video. Okay. Are you ready? So I get this point. Here, if it's funny, it's just keep calling the last one, and it's why because it's working like pop 1, pop 2, pop 3, pop 4, pop 5. Yeah. Okay. A more useful example. Okay, what was my? Let's go back to the topic. I had like the problem because we right now returning nothing actually, right? We're returning here nothing. But if we terminating the condition, it's still finishing that off after that, right? If we have this termination, we're still calling that one, and then we're clearing the stack. Correct? Is it working like that? Yeah, it should work like that. Just say yes. And we have the LIFO scenario. So that's why 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. How it's gonna work. Count will be 5, so it will be a 5. What is it? What's up? It was you, right? We're gonna. What's up? I got roasted today. One question: am I understanding this here correctly? Is this? Am I getting it correctly? That if it's getting terminated, we're just gonna call that one then, right? So we're taking the plate, right? We putting up the plates, right? And then we have the termination. So we're taking the plate. But first we have to finish this one then, the pop. And then we're taking the plate away from the stack. And that's why we have then 5, 4, 3, 2, 1. And then 1, 2, 3, 4, 5. Correct? So let's keep going. It's worth noting that the push outputs happen in the forward order since they occur before the recursive function call. The pop output occurs in reverse order because they occur after the recursive function call, as the functions are being popped off the stack, which happens in the reverse order that they were put on. or more useful example, know that we have discussed the basic mechanics of recursive function calls. Let's take a look at another recursive function that is slightly more typical. I would say the else is the terminated condition. Okay. Okay. So it's more like, is it more like, no wait, this here is the, we have this condition, so we're jumping out and then we're doing that call and it will be then 1, 1, right? And then we're pushing this out and then we're taking the next thingy. We have the same being it. Okay, I think I got it. Okay, useful scenarios. Sum 2, integer sum 2. So we have returned the sum of all integers between 1 inclusive and sum 2 exclusive. Inclusive. Okay, return 0 for the negative numbers. Procedural language feel like a bad choice for learning recursion. What kind of language you program, by the way, Nix? So, okay, we have this. By the way, what's up? I just realized I read the article because you tuned in a little bit late. The stack and the heap, and I realized that was a really good description how the stack is working. Actually, you have to know a little bit about the stack to understand how the recursion stuff is working in C++, right? And that was my problem. Learning C# currently, Java, C++. Nice combination. Why you want to learn C++ if you're learning C#? I mean, hey Rip, how you doing? Okay, keep going. In 1999, okay. But see, it seems like C++ is getting even better, right? A more useful example. Now that we have discussion the basic mechanics of recursive function calls. Let's talk. Okay, we have this. Okay, let's see. Okay, we have. Sorry, guys, that I'm repeating that again. Okay. Sum 2, and then we have if it's smaller equal 0, return the 0. Correct. Okay. If sum 2 is equal 1, return 1. Normal base case termination condition. And this is also a termination condition. And then we just say return sum 2 minus 1 plus sum 2. Recursive function call. Wow, interesting. Keep doing this until this is happening. Then we're returning a 0 or 1. Makes sense. I started on the Apple Basic 2. Nice. Nice recursion, right? Recursive programs are often hard to figure out just by looking at them. It's often... Oh, wait, I have to see. Recursive programs are often hard to figure out just by looking at them. It's often instructive to see what happens when we call our recursive function with a particular value. So let's see what happens when we call this function with parameters sum to 5. So sum to 5, then we have 5 is bigger equal 1 is false, right? This is not so we return sum to 4 plus 5. What are we going to do? Really interesting. Wait. Because yeah, okay, makes sense. Wow, this is interesting. Yeah, that makes sense. Yeah, it makes sense. Okay, everything is clear. Sum to 4 called, and we keep going like this. Return false, false, false until we reach return 1. This is a termination condition, so we just bring it. Yeah, that's it. Now we unwind the call stack, popping each function off, and we're starting with the first last element what we added, right? LIFO. So we're gonna return the 1. And then we have sum to 2. And that is 3. Sum to 3, 6, 10, and 15. Functional programming. Oh man, this is so... Yeah, now it's perfect time to start with monads. What is this? But 8 years of use army service now and veteran took me away some, and now working on my bachelor's of science in software development and writing RPG games for Discord. That's cool. That's really nice. That's pretty nice. I mean, I'm 35 years old. Have no bachelor, nothing, right? I'm just self-employed and learning C++. Yeah. Oh, you're 93. That's really cool that you went back to school. I mean, I got is it that I got so roasted. Post and pre-increment things. Okay, this is also interesting because if you had that one, if turning it, we're starting with 1. Well, I'm right now a little bit on 1. Okay, that makes sense. Yeah, we added this here. What we're calling else then. So we're getting something bad, right? So we're getting back the 1. Return 1. So we have the 1, the sum to 1. The sum to 1 gives us what? Yeah, return 1. Well, that's like a toxic recursion thing, right? I think recursion can be really toxic, to be honest. Then we have it with the 2, right? And then we're getting this value, yeah, sum. We have the 2. I mean, this is... I know recursions are sometimes a little bit special. I'm getting this, so we're going in and then we're taking this stack. So that's what we're getting back then. And what we're getting back from the 2, this returns the sum to 1 plus 2, correct? Which is then 3. I'm right now confused. Because we're just returning it here. Okay, got it. Here we're getting the values then. So the value will be 3, 6, 10, 15. 4 plus 6. So guys, maybe I have a nice project idea. So for all the C++ programmers, maybe we should start program like a web shop in C++. That would be a nice challenge, right? Okay, we're doing it with the 1, yeah, and then we're doing it with the 2. So we have sum 1. The real one is TS in any app below. So you can easily run into the same problem as, okay, so if you put in 5. I think you have to practice recursion to get better, to visualize it, right? Is it normal like that? It's in the beginning a little bit confusing. I mean, it feels like I have to actually. I plan today to go climbing, and yeah. Eight Queens of Death problem pause. Then have you already done the Towers of Hanoi? It's a really nice recursion problem. Oh, nice, guys. Okay, let's keep doing. Guys, you know that I have to rewrite my first exam in computer science. I'm gonna write a computer science 2, and I have to write computer science 1. But for computer science 1, I will have another professor. And I just figured it out. What he's doing, he's just showing one code, and you have to write down you have to correct the code by via paper. That will be fun. So what's backtracking? So at this point, it's easier to see that we are adding numbers between 1 and values passed, both in inclusive, because a recursive function can be hard to understand by looking at them. But I want to understand them, boys and girls. Good comments are particularly important. Note that in the above code, the recurs with the value sum 2 minus 1 rather than minus sum 2. That's pre-incremented, right? We do this because operator minus minus has a side effect. Oh, wait a second. We do this because operator minus minus has a side effect, and using a variable that has a side effect applied more than once in a given expression will result in an undefined behavior. Is this again this topic about is this the same topic about like what we had before? Yeah, I have to do it on paper. Yeah. I have to redo my exam on paper. It's really nice. Super nice. No, different topic. Okay. Then it's everything. Okay. What is the side effect then? What is the side effect? And using a variable that has side effects applied more than once in given expression will result in an undefined behavior. No, we're getting a wrong code and we have to correct it and we have to show what is wrong in the code. And we have to write it on the paper. And I saw today like an example and the code was like so wrong that it was like completely annoying. It would be just easier just to rewrite the full logic, you know? Okay, recursive algorithm. Recursive function typically solve a problem by first finding the solution to a subset of the problem recursively, and then modifying that sub-solution to get a solution. In the above algorithm, sum to value first solve a sum to value -1, and then adds the value of variables value to find the solution for sum to value. In many recursive algorithms, some inputs produce trivial outputs. For example, sum to 1 has the trivial output 1. You can calculate this in your head. Yeah, and does not benefit from further recursions. Inputs for which an algorithm trivially. Okay, this is a new nice English word for me to learn, it seems.
Trivially.
Trivially. Oh God, 19.
Trivially.
Trivially. Oh my God, English is also was trivially. Oh fuck. Yeah. It produce output is called as a base case. Base cases act as a termination condition for the algorithm. Base cases can often be identified by considering the output for an input of 0, 1, or null. Fibonacci numbers. Here we go. One of the most famous mathematical recursive algorithms is the Fibonacci sequence. Fibonacci sequence appear in many places in nature. Or some people say like in business environment also, like in stocks and stuff like this. Never worked for me so far. Such a branching of trees. The spiral of shells, the fruitless of the pineapple, and uncurling fern front. Here's the picture of the Fibonacci spiral. Stocks bad. Yeah, I know. It seems stock is not nature, right? MATLAB is a piece of guys, I was today like in university, right? You know, and I had like really the feeling maybe I should not do university anymore. Maybe Twitch chat is enough. I can't. You know, because of you guys. You are better than the most professors, right? It's just the truth. I mean, Twitch is bigger, man. Here's a picture of Fibonacci spiral. I mean, I learned a lot from you guys. To be honest, I learned a lot from you guys. I learned from you more than in university. Not like in programming. In programming, I learned more than in university. Each of Fibonacci numbers in the length of the side of the square that the number appears in. Fibonacci numbers are defined mathematically as a function of n, 0 if n is equal 0, 1 if n equal 1, function n minus 1. Okay, so on. Okay. Back from work. Welcome back. So when are we doing math? Should I do also like a math stream? We could do it. I have still from you know, back then I studied automotive system engineering, and we had a really good math professor, like a decent one, really good one. Actually, one day I want to relearn all the stuff there. I mean, you could do it on stream if you want to. Consequently, it's rather simply to write a not very efficient recursive function to calculate the Fibonacci numbers. Not very efficient. I hate these statements in C++ or in programming. It's so nice. Like this, like always, like consequently, it's rather simple to write a not very efficient recursive function to calculate the Fibonacci number. So Fibonacci, blah blah blah. Now we have this all the statement, base case, termination condition. Then we have again this okay, and then we have Fibonacci count -1 plus Fibonacci. Kannst du sowas auch machen? Oh, you can something like this. Oh, okay. Oh, my brain will, of course, will like it. My brain will like it. 100%. My brain is gonna like this. Oh yeah, this is Beautiful. And the main program to display the first 13 Fibonacci numbers. And then we're gonna, and we have a for loop, so we're gonna call it, yeah, okay. And it's gonna call it itself, and then we say count -1, and the other thing we're gonna say count -2. Then we gonna, this is gonna work. This is funny. So we're first doing that one, right? And after that is finished, blah blah blah, we're doing the other one. And then we're returning it. If we're hitting the base termination condition. Filling it up, and then we're taking it. I'm not, guys, to be honest, I'm not gonna try to visualize this. Right? If you keep going. Kosara algorithm mega broken, reduce the complexity of a lot of graph theory problems to find the strongly connected components. I think for if you want to be like in tech and stuff like this, math is really important, right? If you want to go into tech programming or stuff. At least if you grind lead code or stuff. I think at some point I want to just do lead code to get some practice, right? And some people saying it's not worth it to do lead code, but I want to do it, right? It seems like everyone says you have to do it. Lead code is not good. Probably it would be super fun to lead code. Yeah, okay. I'm doing my own project and I'm gonna do lead code. Are you now happy? Are you now happy? I just want to learn the concepts, what you can learn in lead code. Running the program produced the following results: 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 142. So what I want to do, instead of checking this, I'm trying it maybe off stream to write it my own understanding. So, Mimo, was ist das hier, bitteschön? Which you will know are exactly, okay, so now we can, new English word just appears.
Memorization.
Memorization, so that was wrong. Algorithms, okay. The above recursive Fibonacci algorithm isn't very efficient, in part of because each call to a Fibonacci non-base case result in 2 more Fibonacci calls. This produces an exponential number of function calls. In fact, I don't know how to pronounce it. So, is it fact or fact? I don't know. The above example calls Fibonacci 1,205 times. There are techniques that can be used to reduce the number of calls necessary. One technique called memorization. What, memorization, or what is it? Is this even a word? It is. Right, how to pronounce it?
Memoization. Memoization.
Memorization. You said it right. Is it memorization or memorization? I do a project at work, lead code in my free time for fun. Yep. Good evening, everyone. Good evening, Raven HS. You said it. Okay. It always the question what your goals are. Many tech companies have you do lead code like the truth is, in Germany, if you want to get a job in tech or something, you need most of the time like a bachelor or a master, a degree like that, you know. Imagine if I would. what does this mean? So wait. Imagine if I write an application, guys. after 1 year with you in C++ with my journey, right? I'm just writing a application, and then I say, okay, my skill is no university, but I learned from Twitch chat. That would be so funny. Catches the result of expensive function calls, so the results can be returned when the same input occurs again. Is it memorization or memoization? I don't know. Is a memorization version of the recursive Fibonacci algorithm? I'm not gonna. You would hire me. I think the rest would not hire me though. So run of this code count is now a stud size t to make indexing the stud vector easier. We will use the static stud vector to cache calculated results. Interesting. If we wait, I could do it also for I could do these things. I could do it also for my merge sort, right? If we have already seen this count, then use the cache result. I was actually asked to do some array manipulation stuff during the application process. What is the statement then? Like, I mean, you mean you studied computer science, and then they ask you to just manipulate how to call it, do a manipulation manipulate the array, like really basic stuff or what? Otherwise, calculate the new result and add it. So pushback Fibonacci count. Okay, then we have the same. Okay, and we have what we have. We have a static. That's really interesting. And we have a size t sound. Okay. Count is now stud size t to make indexing stud vector easier. This is also. Use the static vector to cache calculated results. This is also 0 and 1, and then we're going to use this static. Yeah. Okay, got it. Interesting. Okay. Even though I have a bachelor, they wanted to test whether I at least had some qualification, know what I was doing. Was it an easy one? Like just change the things in the arrays and that's it? The point I made last stream about pre-increment, post-increment, it's about forming a good habit of expressing that you actually want. Don't write code that does unnecessary work. When you're deep in generic code, type of I can be whatever. When I heard someone pros up optimization as an argument, they're kind of missing the point. Yeah, I got roasted today, like heavily. I just said, no, I'm not gonna start again with this. I just said there's some cases that can that if you're using like if you're using I++ instead of ++I, that you could produce an overhead. Recursive versus iterative. And I got roasted for the statement. Recursive versus iterative. One question that often asked about recursive function is why use a recursive function if you can do many of the same tasks iteratively using a for loop or while loop. It turns out that you can always solve a recursive problem iteratively. However, wow, this is a strong meaning, always. For non-trivial problems, the recursive version is often much simpler to write. Ah. And read. For example, while possible to write the Fibonacci functions iteratively, it's a little more difficult. Try it. Okay, here we go. Iterative function. Those using a for loop or while loop are almost always more efficient than their recursive counterparts. Oh, interesting. Okay. This is because every time you call a function, there is some amount of overhead that takes place in pushing and popping stack frames. Iterative function avoid this overhead. The problem was I had to remove duplicates from a sorted array. Wait, this is easy, right? Oh wait, let me think. Duplicates numbers or what kind of stuff you want to remove from the array? Can you be a little bit more precise? The numbers were already sorted. I mean, then you just have to store it like temporarily, and then say, okay, if I have this number, I have like a number or something. No way. So you could just iterate through that, and if you say, and then you can save always one number, right, temporarily, and then you check if you're getting it with the next index. If yes, it's a double number. So jump to the next one. I mean, probably something like this was your solution, right? What? And you studied like computer science, and then you was like, okay, I will take it. Nice, I'm gonna take it. Iterative function avoid this overhead. Okay. That's not to say iterative function are always a better choice. Sometimes the recursive implementation of a function is so much cleaner and easier to follow that incurring a little extra overhead is more than worth it for the benefit in maintainability, particularly if the algorithm doesn't need to recurse too many times to find a solution. In general, recursion is a good choice when most of the following are true. The recursive code is much simpler to implement. The recursion depth can be limited. For example, there is no way to provide an import that will cause it to recurse down 100,000 levels. Wait, the problem is if I have a recursive call, right? And if I have a limit, something, right? Like termination value. But the problem is I could end up to overflow it, right? The stack. Or am I wrong? The iterative version of the algorithm required managing a stack of data. This isn't a performance critical section of code. Ja, was soll ich dir erzählen? I mean, yeah, nice. But probably you would not get this job offer if you not studied, right? But probably your studying was really damn hard. However, if the recursive algorithm is simpler to implement, it might make sense to start recursively and then optimize to an iterative algorithm later. Best practice. Generally favor iteration over recursion, except when recursion really makes sense. Okay, good to know. Quiz time. That's like if I'm going to bed, I'm doing this quiz time stuff. I would say, guys, now is YouTube time. Let's do this here weekly. Oh, I'm so ready for this. I deserve this. Right? That.
And welcome to C++ Weekly. I'm your host, Jason Turner. In this episode, well, I think it's time.
So he's doing every week an EP? Really? Holy moly. And he have already like 300 something?
Time to discuss the difference between I++ and ++I.
Nice intro, by the way.
This episode of C++ Weekly is sponsored by me. Be sure to check out the video description for important links about upcoming events.
What?
Sponsor to check. This episode of C++ Weekly is sponsored by me. Be
By me?
sure to. This episode of C++ Weekly is sponsored by me. Be sure to check.
This is so good. This is so good.
Check out the video description for important links about upcoming events, sponsoring the channel with Patreon, buying copies of my best practices and puzzler books, and how to contact me if you are interested in on-site training or remote code reviews. Now, I see these two constructs used
Just convert it into an ordered map. True, you can do this, right? Yeah, which language you used for it?
interchangeably, but they actually have quite different semantics. And I think it's important to understand the difference in the semantics between them, as well as understand any difference in your code generation plausibly from using them. So let's just go ahead and look at this example where I have an int I equals 0 and
Oh, you have a lot of stuff here. You see this? Oh, that's getting interesting.
I am returning I++. And I get that the program returned 0. So
Yep.
I had I and I incremented it, but I got 0 back. Why did I get 0 back? Let's go ahead and swap these pluses over to the other side. And we'll see that the program now returns 1. So let's go ahead and dig into
Since I applied for a role as a front-end developer, obviously JavaScript CAC. -1. Oh man, I don't know if a programming job is even fun. I think that there can be jobs that are really, interesting, but I think there can be like also really bad jobs out there, for programming. I mean, if you have, for example, a manager or whatever, and you have like no understanding about how hard some stuff could be to get implemented, and they're just saying, yeah, you have like 4 or 5 days for it. Go for it.
this. First of all, this construct, ++I, is known as pre-increment. And this construct is known as post-increment. And they actually have kind of goofy ways.
I know friends kind of fly me for earning more than them while sitting in a home office all day, but coding can be really frustrating. I think coding can be really frustrating, right? I mean, I think coding can be really... Maybe you can even build up an anger problem, right? I at least suffer 1 mental breakdown per week. Yeah, I think coding is not easy, right? Maybe sometimes the coding part is not even like the difficult thing, just to find a solution for the problem. I mean, I have every day with you guys a mental breakdown, right? Just to be real.
Of defining them if you are implementing your own pre-increment and post-increment operator overloads for your own user-defined.
I mean, last time we were starting with that merge sort thing with recursion, I even dreamed about it. It was not good. It was really not. It was a little bit too much.
Type. And let's go ahead and make a very simple wrapper around an int.
I don't know what my dream was. It was really weird. It was like I was sleeping and waking up in a loop, something like this. It was. You know, the merge sort thing in this kind of logic in my dream? That was so weird.
Int. Now let's go ahead and define our own operator plus plus. Now this currently has a compile error because we need to discuss which operator we are defining and what that means. We are defining, in this case, the pre-increment operator.
Okay.
This is the plus plus I version. And pre-increment returns itself back. So we're actually returning a reference to an object of type myInt.
Can we say this is an assignment operator? Yeah, right?
And this really should be const expr. Implementing this
is wrong. But thanks God, our lead dev is a really nice guy who gives a lot of feedback plus instruction when needed. Okay.
Is pretty straightforward. We just pre-increment our value and then return back a.
Is it always like that the what you said, like the lead developer is like a five head? Is it always like that?
Reference to ourselves.
Are we using context?
So now if we have an object of type myInt, and let's go ahead and initialize it with 1, shall we say. If I call this pre-increment, I have just now incremented my internal value. And if I were to return my now confusingly named value.value, I should see that yes, I get to returned. Let's go ahead and comment this out because I have incremented the value from 1 to 2. Pretty straightforward. Now, if I wanted to call post increment, this isn't going to compile because I haven't defined a post increment.
Yep,
now, the compiler actually gives us a clue. Earlier compilers, this would have been much harder to.
You have these things not in Python, right? Do you have these overloading things in Python and in the other languages?
Figure out. To implement the post increment, it looks like this.
Python, yes, okay.
Now this dummy int here, that thing int, it has no meaning. It exists simply as a way to distinguish between pre-increment and post-increment. So now I want to call val plus plus. No, that's not right. This doesn't do what it should. So note I'm returning a copy here. This is actually quite intentional. Now this compiles because the compiler doesn't know the semantics of what we're trying to do. It just lets us do whatever we want to do inside this. A proper post increment needs to do this. First of all, we need to make a copy of our current state. Then we need to increment our current state.
Yeah, be creating a copy.
Then we need to return that copy, the previous state. And this is where things are weird. So a pre-increment says, increment the value and return the new value to me.
Exactly.
Post-increment says, increment and return the previous value. That's not generally what we mean. How often in our code do we actually mean, oh, excuse me, I would like the previous value here? No, we never want that. We almost always, I say never, someone's going to correct me, we almost
It's so nice. It's so nice, you know, like
never mean give me the previous value. There are certainly use cases for that, but when you see something like this, I would argue that this is nonsensical. On each
I did also.
I
got roasted for it.
I and then return the previous value.
Yeah, I did this also. Yeah.
In some cases, this is actually expensive to do. And
I
we
said
can
it.
show
Yeah.
where in
I
a
got
couple of
roasted.
places here. What we almost always mean is simply increment I don't care what you do with that return value. This copy that has to occur of the previous state has got to have some impact somewhere, right? So let's go ahead and just take a quick look at where that might have some impact. And I've tried to come up with some examples for how we can really look at just the impact between pre-increment and post-increment. And I think I have some ideas, so let's go ahead and see how this looks.
Oh,
I'm not using a template here like I normally would for code like this, because we want to see the actual full generated code here. Now I'm going to go ahead and I'm going to get rid of this body of main because I don't want that getting in the way. And we are going to shut down this output so we can look at just the assembly that has been generated. So I'm doing a simple loop from begin to end of these two map iterators that were passed in. Start with a result of 0.
Oh yeah, nice.
And for each element in here, I just want to add the value, not the key. I'm going for just the value. So I'm getting the second element here. That's an iterator. I need to do that. And then I need to return result. Now, this code isn't doing anything here because it becomes an infinite loop because I forgot to increment my begin iterator. I'm going to start by doing a pre-increment, and we'll see what this code looks like. Okay, this is 26 lines of assembly, and we can see that it is calling this tree increment function. And this is with pre-increment. Now, if I make it a post increment, and we have to keep in mind that now we're having to copy this iterator, we see exactly the same code generated. And this is because we have optimizations turned on. And generally speaking, the difference between pre-increment and post-increment from a performance standpoint is going to be meaningless when we are in an optimized build. Let's just go ahead and disable the optimizer for a moment. Okay, so it is a very subtle difference here with this code. We went from 95 lines of assembly with an optimized build disabled with pre-increment to 100 lines of assembly if we do a post-increment. It's a...
what is he using this above the... No, not really, no? Oh, it's defined right. No, it's another one. Okay, this is really interesting.
Small thing, because generally speaking, our iterators are very cheap to copy. So it only has to keep track of just a tiny little detail that it is then returning back to us a copy of it. And that's a good thing. We want our iterators to be cheap to copy. But there is a difference. So I'm going to now show you some code that I had created earlier that tries to show just the difference between pre-increment and post-increment. So we have a function that returns a const iterator to us for a map from int to int. I have this side-by-side comparison diff viewer feature that Compiler Explorer supports, and I am building both with optimization disabled, and I am using Clang. trunk, C++20 mode. I have pre-increment and post-increment. The left side is the post-increment. That is the one that should be generating more code. And the right side is the -D pre-increment here. So again, we're seeing a difference of only 6 instructions. It is not going to have a huge impact on your code, even in a debug build. Although it might be the kind of thing that if you have many templates stamping out code, that you would end up seeing a large impact. The thing that I really want you to focus on, though, is the fact that if we do a pre-increment, we increment and we return the new result. If we do a post-increment, we increment and return the previous result. If I'm reading code, I++ raises my eyebrows. Why do we need this previous value? And this should be, generally speaking, if we see ++I, we know we're incrementing a value and we're using that new value. If we're doing I++, then we're asking why. This is my take on this. I'm certain there will be people who disagree with me in the comment section of this video, but I think I've made my argument for one being, generally speaking, the one that you want, the other one being unnecessary complexity and unnecessary cognitive overhead while we're reading the code. So again, thank you for watching this episode of C++ Weekly. I hope you got...
That was so good. That was so good. Save that. Oh,
something.
yeah. I've been trying to get people into the habit of always using pre-increment unless they need post-increment. Not being easy. The iterator used to demonstrate a big effect would be a map. True. Let's see what people are writing. The default code snippet from the Visual Studio will apply for a loop using the I++, but you're right. The pre-increment is better than most cases. It's a shame that compilers can't just optimize it into a ++I when it doesn't make a difference regardless of the -O flag. Between pre and post. Yeah, okay, that makes sense. So C++ should have actually been named ++C. Oh, that is so good. Is there a difference compared to C if you have this increment stuff? Not really, right? Mm-hmm. Mm-hmm. Unnecessary cognitive overhead was the most important phrase in this lesson. I try to avoid that all the time. Furthermore, if the, even if the compiler optimization is good, I guess it's better to have a code closer to what we really want for semantic. The syntactic, it makes not that much difference then, but also to improve compilation performance, compiler does not have to optimize I++. True. That might be meaningful on large code bases. Mm-hmm. Mm-hmm. Okay. It seems also it's kind of a deep topic, right? It is, right? So what is the time? Yeah, 2 hours 21. I mean, we can still do some talking if you guys. Yeah. Okay. Should I check another video or something? I think I have still some videos to watch. Let's see. Google phases out cookies. This is already known. Really, a really long time. I think I will bring it to the end for the day. How are we gonna rate? Who's online? We gonna rate. Wait, he was. Tim. We're gonna rate Tim. So thanks a lot for yeah. Thanks a lot for watching my stream today. Thanks a lot for the help, and I wish you a nice evening. I'm out.